Welcome all. This is a TCS seminar at Jagiellonian University. Today our speaker, because not guest, just speaker, is Bartosz Walczak. Bartek will talk about Burling graphs, something that is of your interest, well, more interest recently, but this is something that is around our group within last, we can say, 10 years. The floor is yours, Bartek.
Thank you. I am grateful to the organizers for letting me speak at this.
The floor is yours, all of it.
At this prestigious seminar. So what I'm going to talk about is a paper on a clique game and the Erdős-Hajnal problem on high-chromatic, high-girth subgraphs, which is to appear at SODA next year. And this is joint work with Seth Petty and Gabor Tardos. So for the introduction, well, we probably all know the notion of a chromatic number of a graph. So, and we know that it is very easy to force large chromatic number. It is just enough to have a large clique, like a large complete graph has large chromatic number. It is slightly less trivial to have triangle three graphs with large chromatic number, but again, still quite easy and classical constructions exist. And it is also known that we can have large chromatic number even if we forbid short cycles. Yes, so there is this notion of a girth of a graph. So girth is the minimum length of a cycle, or infinity if there is no cycle in the graph. And Erdős in maybe I will not write it. Erdős in 59 proved that using the probabilistic method that there exist graphs with arbitrarily large girth and arbitrarily large chromatic number. So this was just a probabilistic proof. Then there were, later there were explicit constructions of that. And in the 60s, Erdős and Hajnal raised the following question. Can we find arbitrarily high girth, high chromatic subgraphs in any graph? Yes, so can we find such high girth, high chromatic graphs as subgraphs of any graph, provided that it has sufficiently high chromatic number? Okay, so let me introduce this parameter f of kg, or maybe gk. Let me define it as the maximum chromatic number of a graph G such that every subgraph of G with girth at least small g has chromatic number at most k. So this maximum theoretically could be infinite. Yes, we allow infinity for the definition. And the question of Erdős and Hajnal, which is now more often referred to as a conjecture. So one of the conjectures of Erdős and Hajnal is that f of gk is finite for any g and k. So if we know that all subgraphs of high girth has small chromatic number, then the entire graph has bounded chromatic number. Okay. Also, I want to stress that this condition is about subgraphs which are not necessarily induced. If we look only on induced subgraphs, then this, like the analog notion, could be infinite. Okay, so this is a problem from the 60s, and what is known, there is basically just one result by Redl from 1977, which says that f4k is finite. okay, which can be which can be said in a different way as follows: whenever we have a graph with sufficiently high chromatic number, that it contains a triangle-free subgraph with high chromatic number. Yes, triangle-free means that the girth is at least 4. So starting from G, let me write that the conjecture is open for G at least 5. Maybe let me show you this proof, because it is very nice, simple, and it gives us a specific function which I think is, which will be repeatedly appearing during my talk. So for the proof of this result, I'm going to define another function. Maybe let me call it phi. So it has 2 parameters, k and l. So this will be the maximum chromatic number of a graph G with clique number at most L, such that every triangle 3 subgraph of G has a chromatic number at most K. Yes, so we are bounding the clique number, and we are bounding the triangle 3, the maximum chromatic number of triangle 3 subgraphs, and we are looking for the maximum chromatic number of such a graph. So notice that if a graph contains a sufficiently large clique, then by Ramsey's theorem, okay, maybe not by Ramsey's theorem, but if it contains a sufficiently large clique, then we can just take any triangle 3 graph with chromatic number greater than K, and if a clique is sufficiently large, then we will find this graph as a subgraph. Okay? So basically, this second parameter is unnecessary for having a finite bound. However, it will help us for the induction in the proof. Yes, so the proof works exactly by introducing this parameter, and now it goes as follows. So this is just K, because if the clique number is at most 2, then the entire graph is required to be triangle 3 by itself. So the chromatic number cannot be greater than K. So now we are going by induction on L. So we assume that we already have a bound of phi KL minus 1, and we want to get a bound for KL. So what happens is that we are arranging the vertices according to some linear order, which is arbitrary. And for each vertex, we are looking at the back neighbors of that vertex. So if the entire graph has clique number at most L, then this back neighborhood has clique number at most L minus 1, which means, and of course, every triangle 3 subgraph of this is a triangle 3 subgraph of the entire thing. So this back neighborhood is colorable with that many colors. Yes, the vertices can be colored with those colors. And now, if we have we fix a set of colors, we fix some set of these colors, and now whenever we have a vertex, which in this coloring of a back neighborhood is colored, say, red, we are copying the color of this vertex into this edge. Okay, so to say it in another way, the color of an edge is defined to be the color of a vertex in the back neighborhood coloring of the right endpoint of that edge. So this way, we have produced some coloring of the edges of a graph with that many colors, And let us notice that if we focus on the graph, which is on the subgraph, which consists of just edges from one color, then we cannot have a triangle. This is not possible in one color. Because what would that mean? It would mean that if we are looking at the back neighborhood of this vertex, it would mean that this vertex was colored red and this vertex was colored red, but there is an edge between them. So that was not a proper coloring of the back neighborhood. Okay. Therefore, the subgraph, which consists of the edges in any single color, is triangle 3. So by our assumption, it has chromatic number at most k. And now we use just the classical fact that if we have split the set of edges of a graph into some number of subsets, and each of those subsets is k colorable, then the entire graph is k to the power the number of these subsets, which is this, colorable, because we can color with tuples, yes, and every coordinate, at the ith coordinate, we are using the color of the graph consisting of edges in the color number I. Yes, and this is a proper, such a coordinate-wise coloring is a proper coloring of the entire graph. So what is this function? We start with k, and every next step we are getting this. So this will be a tower of k's of height, which is something like L minus 1. Yes, so our function, okay, I should write that it's not necessarily equal, but it is at most this, and maybe for simplicity there is this arrow notation for towers, because I will be writing many towers during this talk. So let me also introduce this notation for such a tower. Okay? So now, when we are going back to Erdős theorem, we can write that this is at most the tower of height big O of k squared log k, because this is the smallest size of a triangle-free graph with chromatic number k, or k plus 1, by well-known theorems from extremal graph theory. Okay, so anyway, we have a tower type upper bound, and this is basically everything what is known in general about this question. So all lower bounds which have been known so far are kind of trivial. I'm not aware of any non-trivial lower bound. By trivial lower bound, I mean a lower bound in which this host graph is just a complete graph. So we are not looking for high-girth subgraphs in some complicated graph, but just for high-girth subgraphs. Okay, so one of the main results of this work is that we can provide a tower type lower bound for F5K. We don't know whether this is finite, but we know that if it is finite, then actually it has to be large. So this is the tower of 2's of height, which is k minus a constant. This is the lower bound that we are getting. Okay, but let's go back for a moment to Erdős theorem, because it tells us that if we want to look for a potential counterexample to this conjecture, then it is sufficient to look at triangle-free graphs, because whenever we have a graph which has so we want to find a graph with very large chromatic number, such that all high-girth subgraphs have small chromatic number. But we know that inside that graph, we will always find a triangle-free subgraph with large chromatic number by Erdős theorem. So maybe we can just restrict our attention to looking for triangle-free graphs as potential counterexamples. And then it makes sense to look what happens for some known constructions of triangle-free graphs with high chromatic number. And it is known that Kneser graphs, Zykov graphs, shift graphs, Mycielski graphs, they do satisfy this general Erdős-Hajnal conjecture. So they do contain high-girth, high-chromatic graphs. And perhaps my favorite construction of triangle-free high-chromatic graphs is the construction by Burling from 1965, which was already used to disprove several conjectures. So why not try Burling graphs as a potential counterexample to this? So this is what motivated like this research. We ask a question whether Burling graphs contain, say, girth5 high chromatic subgraphs. So it turns out they do, but it turns out that we are getting this lower bound exactly for Burling graphs. So it is not that easy to find such girth5 subgraphs of Burling graphs. Okay, so maybe let me go to this one. So what are Burling graphs? What is Burling's construction? 1965. Let me define it this way. So I will be constructing the graph itself, but also with some underlying structure of a tree. And the edges of a tree, they are not necessarily the edges of the graph, so I will be drawing them with a distinct color. And also, I will be drawing a tree in a somewhat unconventional way so that the root is on the left and the leaves are on the right, because this will be more suitable to what happens next. Okay, so B1 is just a single vertex, and the underlying tree is just a trivial tree with a root at that vertex. B2 is a graph which looks like this, and in the underlying tree, this is also an edge. And then every next step is defined inductively from B2. So somehow I want to have this B1 for some reasons, but I could even start from the construction from B2. So the leaves in this tree are somehow special, so maybe I will be also drawing them with a different color. So suppose that we have a graph bk minus 1, so that we have this tree. Here we have the leaves of that tree, and now I want to build bk. So what happens is that, okay, for each of those leaves, I'm doing the following operation. I'm temporarily forgetting about this leaf. It had some neighbors in the graph, and it was also a leaf in the tree. So there is some path in the tree going here. We are going to maintain the property that every edge is between the ancestor and the descendant in the tree. So every edge which I'm going here will be to an ancestor. So it will go towards the root. Okay, so let's forget about this guy. And I'm going to draw another copy of bk minus 1. It has its own root here and some leaves. So now for each of those, so these are also the leaves in the tree, but they also have some neighbors here. Actually, this root will always be a neighbor of a leaf. This will be one of the conditions that we maintain through the construction. So for each of those leaves, I'm going to take a copy of that leaf, which will be connected to the same parent in the tree. Okay. So And then there will be one more leaf attached to this. So the red edges, they are the edges of a tree. They are not yet the edges of a graph. So what are now the edges of the graph? So this guy gets edges to all the vertices, to all the neighbors of this. So this is just a copy of this guy. And the same here, 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 and here. They will have edges to those. Now there is an edge between this one and this one. And same here, here, here. And now all these leaves, all these red leaves, they become connected to the neighbors of this guy. Okay, so from all of them, we have a bundle of edges going here, 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 and now this vertex is replacing that vertex which was previously a leaf in the structure of a tree. Yes, so the vertex that inside that tree was the parent of this guy becomes the parent of this one. Okay? And we continue doing this kind of replacement for each of those other leaves of this first tree. So there will be the same kind of replacement here, same kind of replacement here, and same kind of replacement here. Okay?
Just a quick question. Once you do you like all does this you like you replace the root? Sorry, not the root, the leaf.
Yes.
Yes. Does it still have edges towards its ancestors, like the leaf head?
No, this one not.
Okay.
So only the new leaves get edges to all these vertices.
Okay. Understand.
So what can be seen from this construction is that we maintain the property that the graph is triangle free. Okay, so basically these vertices, like if the graph is initially triangle free, then these vertices, because they are in the neighborhood of a single vertex, they must form an independent set. The same here, these vertices form an independent set. And yes, we can see that we don't create any triangle here, right? Actually, there is something stronger, and this will be an important condition. If we look at any path from a root towards a leaf, there are two forbidden configurations. It never happens that we have a vertex with two forward neighbors on that path. And it never happens that we have two crossing edges like that. These configurations are forbidden, and they already imply that the graph is triangle free. I mean, the fact that this is forbidden already implies that the graph is triangle free. Okay, this plus the condition that every edge actually connects an ancestor and a descendant. Okay? And now I want to claim that the chromatic number of bk is equal to k. Actually, I will just prove that it is at least k, but it's easy to see that we can get a k coloring from this construction. Okay, so here it is 1, here it is 2. The base cases are easy. So now let's assume that the chromatic number is k minus 1 here. But actually, I need a stronger condition. I need a condition that for every coloring with any possible number of colors, there will be a leaf with the property that on the neighbors of that leaf, we see at least k colors. This is the condition that I want to maintain.
Can you repeat it?
So for bk, actually, I want this condition. There is a leaf v such that bk, and I look at the neighborhood of v, the chromatic number of that, for every coloring, for every coloring C, not necessarily K coloring, just proper coloring with any possible number of colors. for every proper color in C, there is a leaf V such that the image of the coloring, the image of the coloring of the neighborhood of V has a size at least k minus 1. At least k minus 1, yes. Because this leaf itself has one more color. So this is at least k minus 1. So here it is trivial because, yes, we want 0 colors on the neighborhood. Here we want 1 color on the neighborhood. And here let's assume that there is a leaf such that, okay, so we pick a coloring of this. And now by the induction assumption, we know that there is a leaf such that on the neighbors we see at least k minus 1 colors. This is the induction assumption. So now I'm going to look at what happens in this copy which is attached instead of this particular leaf. So here again we see some coloring. So originally, so among these vertices in particular, because these are the vertices that also form the original copy of bk minus 1, there is a leaf such that all the neighbors of that leaf inside that copy have at least k minus 1 distinct colors. So we have k minus 1 distinct colors here and k minus 1 distinct colors here. If these are different sets of k minus 1 colors, then altogether this is a set of at least k colors. And then this leaf, which is connected, okay, maybe this one, this leaf which is connected to both this set and this set, it sees at least k colors. So the other possibility is that this set of k minus 1 colors is exactly the same as this set of k minus 1 colors. So in that case, this white vertex here has a kth color, which is different from this k minus 1, which means that it is different from this k minus 1 because they are equal. And now this red vertex here, it sees that color and it sees all those colors. So it sees at least k colors. I think I messed up the minus 1 with minus 2. It should be instead of minus 1. So let me maybe change this to, and here we are constructing bk plus 1, and then it is correct what I have said about this construction. Sorry for that. Okay, so this is basically the argument why the chromatic number grows, but more importantly, we know that we see that we have this underlying tree structure and that these substructures are forbidden from our tree structure. So now, since we are interested in subgraphs of those graphs, it would be nice to have some characterization of those subgraphs. It would be nice that we know what those subgraphs look like. And fortunately, we can provide such a characterization. So let me introduce a definition. So say that we have a graph G. So we have a graph G, and we say that T, a rooted tree T, is a tree presentation of G. Okay, if the set of vertices is the same, so T is just a tree on the same set of vertices, then every edge of G is ancestor descendant in T, just like here. And third, the following are excluded. Exactly those configurations there, excluded on root to leaf paths. So this is excluded, and this is excluded. Okay, so we see that those Burling graphs, BK, they have a tree presentation. And actually, a graph has a tree presentation if and only if it is a subgraph of bk for some k. This is the characterization that we need for our result. So let me write it as a lemma. G has a tree presentation if and only if G is a subgraph of bk for some k. And actually, we can say that if G has a tree presentation, then here we can take k equal to the number of vertices of G. If we want some kind of quantitative results, then going this way, this is what we can assume. Okay. I'm not sure whether I would like to spend now time in proving this characterization. It is not difficult. It just requires, okay, one way it is kind of trivial because we see that those graphs have tree presentation and we see that the property of having a tree presentation is closed under taking subgraphs. So yes, when we are removing edges, then it is trivial because we cannot introduce these structures by removing edges. When we are removing vertices, then what we need to do is that, okay, if in the tree, if we are removing this vertex, then basically the parent of this vertex becomes a new parent of the children of these vertices, and everything else is preserved. Okay? So this condition is closed under undertaking subgraphs. We can say that, okay, let me tell you one thing about how this is proved. So the interesting direction is this one. This is the interesting direction. So we can define something that is called a full tree presentation. So full tree presentation means that whenever we have a path from a root to a leaf in a tree, and we look at a vertex that is not the leaf on that path, then this vertex always has an edge forward. So whenever we have a tree presentation, we can keep adding edges greedily by keeping the fact that it remains tree presentation. And at the end, what we are getting is a full tree presentation. We can just see that, okay, if there is a vertex which has no forward edge, then okay, so what prevents us from adding an edge going towards the leaf? What prevents us is when there is such an edge. Okay, so let's take the earliest vertex, which is after this one. So then, instead of an edge to the leaf, we can add an edge going to this vertex. And this cannot get any forbidden structure because, okay, we cannot have anything like that because I took this as the earliest vertex, and we cannot have this because we would have it before. Okay? So when we keep adding edges, we are getting a graph with a full tree presentation. And now when we have a graph with a full tree presentation, then this is actually like having a full tree presentation is equivalent to being connected and being an induced subgraph of a Burling graph. Okay? So basically when a graph has a full tree presentation, then it has like, we take a root. In the tree, we look where the edges go from the root. So now, by our condition that this is forbidden and that is forbidden, whatever is attached here below, this is a cut vertex in our graph. There cannot be any edge going here because that would be a crossing. So we can use, and maybe we have more of these cut vertices, and so on. So we can use the structure of this to and the recursive construction of Burling graph to find this inside this. This is not a difficult task. Okay, and let me skip any further details. Okay, so going back to our work, what we have proved about Burling graphs is that first, okay, if the root sends edges to all the leaves, actually this is kind of an easy case. Okay, but let me show this. Okay, just as easy as the other cases. So the root sends edges to all the leaves. Then basically we embed the root here because, as I said, doing this construction, the root is always connected to all the leaves. Yes, so we embed the root here, and then the other parts are completely independent. So like we look at the children of the root. So one of those will be embedded here, the other one here, the other one here, and here, and so on. And we will have sufficiently many of them. Perhaps the corner case is when we have just a star then we embed the root here, but then maybe we need to take more than one leaf from these guys. But otherwise, yeah, we can deal with that inductively. Okay, yeah, this is basically the idea. If we look, if we want to do it in more detail, that would take some time. So I would like to skip it. Okay. So, what do we know about those Burling graphs? So first of all, if K, okay, maybe let me write it this way. If M is at least, and now comes some tower function of K which is, I think it's just K squared, then Bm contains a subgraph with girth at least 5 and chromatic number greater than K. Okay, so this result shows that Burling graphs are not a counterexample. At least they are not a counterexample for G equal to 5, but we also believe that we can generalize those arguments to any constant G. So Burling graphs will not be a counterexample anywhere. It's just not written yet, so I don't want to. But we are pretty sure that we can do this for any G. But they are not a counterexample for 5. But on the other hand, if M is at most K, and now we are taking, 2 here, and here we are taking K minus a constant, then the opposite of this. So Bm contains no subgraph with girth at least 5 and chromatic number greater than K. So this second statement implies this lower bound because M is the chromatic number of Bm. right? So this implies that F5K is at least two to the power K minus a constant. Okay, so in the rest of my talk, I will try to show you how both of those are proved. And somehow the proof of one can be treated as a motivation for what we consider when proving number two. So let me start with number one. So let me try to show you how to find the triangle, how to find girth-height subgraphs in Burling graphs. And basically, by the lemma, we just want to find a graph with a tree presentation which has girth at least 5. Yes, because then, by the lemma, we know that this graph is a subgraph of BK, and actually it is a subgraph. If that graph has some number of vertices, then it will be the subgraph of B with that number of vertices. Okay? So I would like to start by showing you an alternative way of just finding high chromatic graphs with a tree presentation. We know that Burling graphs have those properties, but I want to show you a different proof of showing that such a graphs exist, and then we will modify that proof to take care of girth 5. The proof that, okay, so what I want to, so we want G with T a tree presentation, and I will write in parentheses, and girth at least 5, with chromatic number, say, greater than K. Okay? So we want both these conditions. Then we know that they are contained in Burling graphs, but for now, I will just show you without the girth condition. Okay? Which is trivial because Burling graphs satisfy that property, but for the, it's important for the method, which is to follow. So we are considering an online coloring problem. In an online coloring problem, vertices, like there are two players, let's call them builder and chooser. So builder introduces vertices one by one, and when a builder introduces a vertex, then builder should connect this vertex. Okay, builder is allowed to connect this vertex to some vertices introduced before, but no more edges can appear later. So when builder wants some edge like this, then this edge appears together with that vertex. Okay, this is a classical online setting, and the chooser, there is some set K of colors, K colors, which we fix up front, and the chooser is required to answer every move of builder with a color. Okay, without knowing how builder will continue. So this is just the setting of the online coloring problem. And now we are introducing a restriction on builder. So basically, let's assume that we have that some vertices have been introduced so far. So when builder wants to connect to some previous vertices like this, by introducing this one, so all the vertices starting from the earliest back neighbor up to this one exclusive, all those vertices become inactive. Inactive, it means that in further play, builder can never connect again to these vertices. Builder can connect only to the vertices that were before and to this one. Okay, but never to those which are here. So notice that by following this rule, builder will never create a vertex with two forward neighbors, and builder will never create a crossing. Okay, and we want to show that still builder can force chooser to lose. When chooser loses when chooser cannot pick a color for this vertex because all colors are already used on the neighbors. This is the losing condition. So the strategy is, for instance, like that. Builder. So what builder maintains is that so builder wants to create. So we are showing that builder has a strategy to force at least k colors, k different colors. Okay, k is a constant, so let's say at least l different colors on active vertices. This is our claim. So like the beginning is trivial. We just put a vertex and builder forces a color on that vertex. And then from L to L plus 1, we go as follows. Builder plays their strategy here. And then builder repeats this strategy here with no connections to builder. Which means that those active vertices, they will still be active after playing this strategy for the second time. And here we have again at least L colors. And now we have the argument which should be familiar from that. If this set of L colors is different from this set of L colors, we have already won. We have provided L plus 1 colors on active vertices. Otherwise, builder presents a vertex which is connected to all these. And this vertex, so now if this set of L colors is the same as this set of L colors, builder forces an L plus first color here, which is now active, and together with these guys we have L plus 1 colors. Okay? And by the way, it is not a coincidence that this is the same, because now we want a graph G with a tree presentation. Let's forget about graph 5 for a moment. So we have a strategy of builder. And the strategy of builder, okay, builder presents some vertex at the very beginning. And now let's say that our K is 2, so we have just 2 colors to follow. We are going to build a strategy tree. So for all possible continuations of chooser, there will be a different branch of the tree. So now there is a red branch and a green branch. What happens when chooser answers red? What happens when chooser answers green? Then, and the same here. Red one, green one, and so on. Okay, so this way we are getting those colored paths which form a tree. Every vertex, which is not a leaf, has exactly one red child and exactly one green child. In general, every vertex will have exactly k children. Okay, maybe not exactly k, because it might happen that not all colors are allowed for chooser at some vertex, because the chooser is restricted by the colors of backward neighbors. So then there will be fewer children, right? Because the chooser cannot answer with some of the colors. And a leaf is when chooser loses. Yes, this is represented by a leaf. So this is a finite tree. Yes, since we have proved that builder can win, there is a finite strategy. So we are getting a finite tree in this way, and now we are embedding a graph. So on any path from a root to a leaf, we are just putting the actual graph which occurs on this path. Yes, so say that on this path, for instance, this vertex was connected to here, then this vertex was connected to this one and to this one, and then this vertex was connected, then this vertex was connected to this one, and to this one, and for instance to this one, and in this moment, chooser lost. So this is the part of our strategy graph on this path from a root to a leaf. And we do exactly the of those paths. They induced common graphs. Yes, because this is what happened in the game up to this point, where the game was common. We are taking a deterministic strategy of building. So that strategy answers deterministically to whatever chooser does. And my claim is that the chromatic number of this graph, which we obtain here, is greater than k. Why? Suppose that this graph is k-colorable. Then chooser will just answer according to the colors of these vertices. Yes, so for instance, if in this k-coloring, this vertex is red, then chooser, when builder presents the first vertex, chooser answers red. Then builder presents this vertex and say that in the coloring this vertex is blue or green, chooser answers green. And so on. And this way, chooser, in some sense, follows this path towards a leaf, because what builder presents with these answers of chooser is exactly the graph which is induced on that path. Yes, this is by definition of that graph. And since we picked a proper k-coloring, it means that chooser will be able to answer every move of builder. So chooser does not lose at the end, which contradicts the assumption that this was a winning strategy for builder. Okay? So this graph which we are obtaining this way, it has chromatic number greater than k, and it has tree presentation, because this is exactly tree presentation. Yes, this is the condition which we have on every path is exactly that this is forbidden and this is forbidden, because this is how builder's strategy was working. Okay? So what can we do now to get this? So first of all, what is the problem with this construction? The problem with this construction is that it could happen that in some branch we are getting a vertex which is connected to these two, for instance, and in some other branch we are also, sorry, not here, but for instance, somewhere here. Say somewhere here. We are also getting a vertex which is connected to this one and to this one, on two different branches of the game. And in our strategy graph, this is a 4-cycle. This is what we want to avoid. And this is not a condition which is local on a single path. So this is not a condition which we can impose on this game. Yes, this is not that we can restrict builder somehow to guarantee that this will not appear, because this is somehow involving two different continuations in our strategy. However, there is a very nice remedy. So when builder introduces our graph in this game, what we can do, whenever there is, so whenever we still have some two active vertices, okay, so say that builder introduced a vertex which is connected to something, say something here, something here, something here. So these vertices, they are no longer active, but this one is, and this one is, and this one is. And now chooser will choose a continuation, whether we go one way or another way. So before letting chooser choose the continuation, builder needs to specify for every pair of those active vertices, or maybe some pairs of them, builder will specify, okay, I want to keep this pair as a possible pair of back neighbors when chooser answers red, but only when chooser answers red, or when chooser answers blue, and only when chooser answers blue. So what does that mean? It means that we are maintaining, like builder maintains during this procedure, some auxiliary graph on these active vertices. Let me use yet another color. Okay, so here we have some auxiliary graph. And after making this move, builder colors the edges of this graph with k colors. So say builder chooses red color for this edge, red color for this edge, and green for this edge. And now when chooser chooses a color for that vertex, say red, then only red edges are preserved in the auxiliary graph. The edges of other colors, they are removed from the auxiliary graph and they never appear again. What does that mean? That means that here, when we go blue, and this edge was colored red by builder, then this move here will no longer be possible. Okay, I forgot to say one more condition. Whenever builder introduces a new vertex and wants to connect to some back neighborhood, this back neighborhood must form a clique in this auxiliary graph. So an edge in the auxiliary graph means it is allowed to connect a next vertex to both of the endpoints. If there is no edge in the auxiliary graph, it means that such a move is not allowed. Okay? So now, when here chooser answers red, then in the next move, builder cannot connect to this vertex and to this vertex, because this edge, since it was colored green by builder in the previous move, it disappears from the auxiliary graph. Okay? Only those edges remain in the auxiliary graph, and then they are colored again and again and again.
Okay, so in this strategy, if you have a graph for the builder, if you have strategy for builder, then this graph of the strategy doesn't have C4. So, but you have to show us that there is a strategy for builder.
Yes, so I have to show that there is a strategy for builder, but now I want to show that there is no C4. This is exactly the case. So why is there no C4? So suppose that in the strategy graph, some C4 would appear. So in general, this C4 needs to look like that. So we are looking what happened when this vertex was played. So when builder played this vertex, and this was an edge in the auxiliary graph, builder was required to color this edge with one of the two colors, or one of the K colors, say green. And then only in the green continuation this edge survives. In the other continuations, this edge is killed, which means that this vertex cannot be connected to both of these. It could be connected to at most one. Yes, so this kind of play, it excludes four cycles. So we exclude the triangles by the fact that this is forbidden. Yes, only this excludes triangles, but also this other condition excludes four cycles, so girth is at least 5. So now I just need to show that there is a strategy for builder. But notice that in order to have a strategy for builder, there is a sub-problem which I need to solve, kind of maybe simpler problem. I need to have a large clique, like a k-clique, in the auxiliary graph. This is a problem by itself. So, okay, in order to force k plus first color, so in order to win, we need to play a vertex which is connected to k back neighbors, which has k back neighbors of distinct colors. So in particular, it has to have k back neighbors. So there has to be a k-clique in the auxiliary graph. And this is not trivial by itself to construct such a k-clique. So this way we arrive at this clique game, which is in the first part of the title. So in the clique game is a simplified variant of this game. Simplified by the fact that there are no white edges. There is only the auxiliary graph. So builder plays the vertices, and whenever a new vertex and maintains some auxiliary graph, and whenever a new vertex arrives, builder connects this vertex to all previous vertices, or maybe we could say that to some previous vertices. This is only disadvantageous for the builder, and then builder is required to two-color these these edges in some way, and chooser just chooses which color should be preserved. And the edges of the other colors are removed. And in this game, we want to create a k-clique. Okay? So first, let's see that we can do this. Okay. So now we are focusing just on forcing a large clique. And let me introduce like two parameters, because I think it's maybe better to have two parameters. So k is the number of colors. And let's have a second parameter, d, which is the size of a clique we want, which is not necessarily the same as k, because k will be fixed and we will be working by induction on d.
Can I try? I think I know, but probably it's stupid. So you assume that you can force d minus 1.
Okay.
And then I'm not sure about this step. Then you play d minus 1 and disjoint d minus 1, disjoint d minus 1, and you do it k times. And then you present the vertex, which sends edges to everything, but in each copy it's one color, yes. And then whatever chooses is.
I think it's more complicated than this, yes, because every vertex, what is the problem? Mm-hmm. When you presented something and you play a new strategy, you are still required to color the edges of this graph.
I was feeling that.
And chooser and this graph will vanish.
Yes,
keep vanishing.
Yes.
Yes.
I see it. Okay, thank you.
This graph will keep vanishing.
Mm-hmm.
So here is what we actually want. We want to construct a large blow-up of a clique in the auxiliary graph. So we want to have many vertices here, many vertices here, many vertices here. We will see how many in a moment. And all edges in between here, all edges in between here, all edges in between here. We don't care about the edges within those sets. So in particular, it's easy to start. Whatever size we want, we can just play like that many vertices, and we don't care about the edges. Builder may just not introduce those edges at all, because this is required to be just an independent set. So what happens next? So we want to extend this. We want to extend the size of a clique, so the new vertices will appear here. And for a clique which is larger by 1, we want fewer of the vertices here. Yes, but there is still some number that we want. So we want to end up, say, with x vertices here. And every time we introduce a vertex, we will be, in some sense, losing some vertices from those cliques. So how we are coloring the edges? Every time we introduce a next vertex, I will show you with just 2 colors. For builder colors half of these edges red and half of these edges green. And now here again, half of these edges go red, but also if these edges go red, then also all edges which go towards here, they are again red. So the color of an edge depends only on the starting vertex. All edges which start at the same vertex, they will get the same color. And all edges which start here and go to the right, they will be green. All edges which start here will be red. All edges which start here, they will be green. And now chooser answers with some color. say green. So what remains? We are keeping just those parts. We are forgetting about these vertices. They will not be useful anymore because those edges have been destroyed. Those red edges have been destroyed. But there is still a lot of edges here. So if we want x edges here, then we are dividing the size of this by k x times. Yes, so basically we have the previous size and we divide this by k to the power x, and at the end we want x because we want just the same that we had here. Yes, so in the other way, going the other way, so let's call this x prime. How many we needed to start with? We need x times k to the power x. And we are repeating this kind of function k times. So this is more or less the tower function, except that we have this k times x times here, but it really doesn't matter. Okay, the strategy has length more or less k, more or less k. Sorry, not k but d, because d is the size of a clique. So k to the power k. The tower of k is of height d. Okay. So this is how we are getting that strategy. And just to show you how we can solve with like the strategy for the actual game that we want, because this was a simplified game that we just want to construct a clique. In the actual game, what we want to construct a large blow-up of a clique with the property that these vertices, they all have the same color, say C1. These vertices all have the same color C2, which is different from C1. These vertices all have the same color C3, which is different from C2, and so on and so on. This is what we want to achieve. And at the end, when we are getting all k colors, then at the end, builder can play. We just need one vertex in each part, and we still want this to be a clique in the auxiliary graph. And then builder will present a vertex which is connected to those colors in the actual graph. And this vertex cannot get a color because all colors appears on the layers. Okay, this is the goal. So how to achieve this? The argument is basically the same. So first of all, to start, we want all these vertices in the same color. So we are just playing a little bit more of those vertices, and by pigeonhole, there will be a large set of the same color, because the set of all colors is fixed. So let's assume that we have managed to do this, and this is in the auxiliary graph. This is a blow-up of a clique. So now what we want to play here, we want to play a large set of new colors. By new colors, I mean colors which are distinct from all of these. And so if we have sufficiently many of vertices with new colors, then again by pigeonhole, they will be a subset with the same color, which is large. And we will get one new color. So how to play a new color? So here we are playing a strategy which is just a full strategy of our game, but with a smaller set of colors. So we do this induction on D, or on the number of colors, but there is also an outer induction which is on the number of colors here, and on the actual set of colors here. So this strategy which we play here forces a color from outside of this set, playing according to our game. Yes, because whenever chooser chooses some color from within this set, then we continue this smaller strategy for a smaller number of colors, And at the first time chooser answers with some colors outside from the set, we reached our goal. And now this strategy.
You play this game locally, but every vertex that you play in the local game have the same coloring of edges outside, because you have to be ready for this chooser to use
yes.
a color that you want. Yes.
So whatever vertex we play here, builder plays here, builder still draws these auxiliary edges to previous vertices, and builder still colors all these previous vertices with now the subset of colors C1, C2, C3. Yes. So with every vertex that we play here, we will be losing some of these vertices. Yes. Yes. But this strategy has bounded size. So we know exactly how many vertices we need to start from here, because we know what is the size of that strategy. So eventually we will get a new color, and then we repeat again to get another vertex with a new color, yet another vertex with a new color, and so on. And as soon as we have enough many vertices of a new color, and this is still large, we have reached our goal.
Then also this color must be the same?
Yes, yes. So we want enough many vertices of a new color so that by pigeonhole, a lot of them will have the same new color. Yes?
I have a question which may seem silly, but like, what is the desired color of the clique? Because we have, like, we color the edges, right? Is there any...
Okay, so chooser colors the vertices, builder colors the edges, but the color of the edges, they are temporary.
Okay.
Whenever builder makes a move, builder colors the edges, and only edges of one color they remain, but then in the next step, builder again color the remaining edges.
So the vertices vanish, I understand.
The edges vanish.
Yeah, but we can never use...
Yes, somehow we can think of those vertices vanishing as well.
We cannot use them.
Because we cannot use them anymore.
So we just need some of the time, like one of... But the clique is colored just in one of the auxiliary colors.
So all these vertices we want to be in one color, say C1. All these vertices we want to be in another color, which is different from C1, and so on and so on.
Okay. And the edges have to just exist in some color.
Yes, and at the end, we are getting vertices in all k colors with a full clique in between. This is a full clique. And when we reach this, builder wins by just making one more move, creating a vertex and connecting to all of these in the actual graph, not in the auxiliary graph, but in the actual graph. Yes, and this is a win for the builder. Okay, so I hope more or less I have showed you the proof of number one, showing the strategy for builder, and like the graph of this strategy will have a tree presentation, and as we have shown here, it will have no 4 cycles, so it will have a girth at least 5. Okay. So now comes...
Where big O of k squared is just like the boundary.
Yes, so if we do the actual counting here, it turns out that the number of moves we need to make this work is this, k is the tower of height big O of k squared. Okay. But this calculation is kind of tedious, so let's skip it completely. And it is not that important that we have k squared here, right? What is interesting is that it's not that far from the lower bound. So where does the lower bound come? It comes from the respective lower bounds on the clique game. So actually, for the clique game, we now have a lower bound. Where can I? Maybe let me continue. Let me continue here. So now we are setting just 2 colors. let's play the lower bound just with 2 colors. And we want to show that chooser can force at least 2 d minus constant moves. So chooser has a strategy to continue the game for at least that time.
So it feels like you're using now the simplification that you have that this representation, like online strategy for builder gives you a graph, gives you a graph, and here you are probably using the opposite thing because you want to show that the tree presentation gives you a strategy, right?
Okay, so let's discuss that first because it's not as simple. So basically, when we have a graph with tree presentation, suppose that we have some graph with a tree presentation. And which has girth at least 5. So no 4 cycles. And there is this white graph somewhere here. So let's assume temporarily that every vertex has at least 2 children unless it is a leaf. So if every vertex has at least 2 children, okay, and this graph has some chromatic number, okay? So let's say that this graph has, this graph has some chromatic number, say that it has chromatic number greater than k. What we can start doing, if there is a leaf which has, the chromatic number is greater than k, yes, so if the leaf has at most k neighbors, somewhere here, okay, actually fewer than k, let's say that strictly fewer than k, then I can cut it off, and the chromatic number is still greater than k. It could not happen that this vertex was the reason for high chromatic number, because if the chromatic number is at most k here, then I would find a color eligible for that vertex after adding it back. So let's keep stripping these vertices. In the leaves. And forgetting about the edges. So when do we stop? We stop when every vertex has at least k back neighbors. Every leaf has at least k back neighbors. Yes, so the leaves are rich. And now let's assume, and the chromatic number is still greater than k, because it didn't change. So now let's suppose that every vertex which is not a leaf has at least 2 children. Then we can forget about parts of those graphs to guarantee that every vertex has exactly 2 children. We just remove excess children. Okay, the chromatic number can go down, but we don't care about the chromatic number anymore because what we need is this condition about the leaves, and this condition will still be preserved for all the remaining leaves. So still every leaf has at least k neighbors. And every vertex now has exactly 2 children. Exactly 2 children. So we color these edges. We have 2 colors, right? So one of the children will be a red child and another will be a green child. We do this in every vertex, which is not a leaf. This way we are getting something like a strategy tree of the k-clique. But it is extremely important that every vertex has 2 children. Yes? So now, once we have something like this, I want to prove that builder can use this tree in order to win the clique game in as many moves, at most as many moves as is the length of the longest path in that. because when builder introduces a new vertex, okay, so chooser will be choosing some colors. So builder follows according to the colors chosen by chooser. And now, when we are somewhere here, and here we have that auxiliary graph.
But you lost the property that you have high-chromatic number.
But I don't care anymore.
And still builder will, okay.
I don't care about the chromatic number anymore. What I care is that every leaf has at least k-children. So when builder wants to make a new move, say chooser chose this path by choosing respective colors for these vertices, and builder now wants to introduce a new vertex. And when introducing a new vertex, builder also needs to choose the colors for all the edges of the auxiliary graph. So whenever we have an edge in the auxiliary graph, we are maintaining the property that this edge is here whenever there is a leaf in that subtree which has edges to both endpoints of that auxiliary edge. But now, when we are at this vertex, by the property that girth is at least 5, such a leaf can exist in only one of the two continuations, either red or green. We cannot have such a vertex in a green subtree and another such vertex in a red subtree, because that would be a 4 cycle. So since it is in a green subtree, builder chooses the color green for this edge. And then when chooser chooses the color green being at this point, then we enter this subtree, and this auxiliary edge still survives. And when chooser chooses red, then we enter this subtree, so this edge is killed, but we don't need it anymore. And at the very end of this strategy, there is a vertex which has actual edges to at least k vertices, and by our invariant, all those edges, like all those back neighbors here, they form a clique, because we were preserving these auxiliary edges. So we still have a clique in the auxiliary graph here, which means that builder is winning the clique game. Yes. So now, if we have a lower bound on the length of a strategy of a clique game, and this graph is too small, smaller than the lower bound, we get a contradiction. The only problem is that after cutting off these unnecessary leaves, and even before cutting off, we may have vertices of degree 1. It could happen that just the entire graph is a single path in the tree presentation. And this argument doesn't work when we have a vertex of degree 1. So we need one more argument to get rid of vertices of degree 1. And it's not entirely, it's not something obvious how to get rid of them, but basically the idea is that whenever we have a long path of vertices of degree 1, then whatever we have here in the actual graph, it is a forest. So those vertices, because every vertex can have, this is not possible. Yes, we cannot have 2 forward vertices on one path. So we have at most 1 forward vertex. So basically, so this is a forest. So there is, so we do some kind of auxiliary coloring in such a way that from each such path, at the end, we can select just one vertex, and we can build this tree that we want here just on these selected vertices. This requires the assumption that the chromatic number is large. Yes, because then we have the tree where we actually, every vertex has at least 2 children and the chromatic number is large. Yes, we use this to imply that those leaves have large back degree. So this is actually also something that we need to do both these arguments together simultaneously. We want that we have picked just one vertex from each of these, but also we want that we have guaranteed that every leaf has a large back degree. And after that, we restrict our attention to just the induced subgraph. We remove excess children, which means that the chromatic number may drop, but we don't care anymore about the chromatic number. And we use the lower bound on the clique.
So what is the lower bound on the clique?
This is the lower bound on the clique. And how does it work? So it works as follows. Actually, the lower bound can be on a much more, even if the goal of builder is just to get a long monotone path of length d, not necessarily a clique, just a path. We already, under this assumption, we are getting the lower. So, how to present it the best way? Okay. So let's assume that we have a strategy which allows builder to build such a long path. Okay, we will be counting vertices which are endpoints of a long path. So say that ni is the number of endpoints, like last points, not the first points, but last points of monotone I paths. So for some number d, we want nd to be at least 1. But let's subtract some constant from d. If we have a path of length d, then we are going to look at nd minus some constant as our starting point. And we know that this is at least, let's say, call this constant, I don't know, c. We know that this is at least c, or even c plus 1. Because this vertex is a good endpoint, but also this one, also this one, also this one, also this one. Okay, the c last vertices, they are good endpoints. So this is our starting point. And now, our goal is that if we have some lower bound on ni, we want to get from it a lower bound on ni minus 1. Starting from this constant. So let me define the following function. Some kind of function phi. This is a function which is changing as the game proceeds. So this function is defined for a specific state of the game. So for a specific state of the game, we have some vertices which are endpoints of I paths. So we have some I paths. And those endpoints, actually those I paths, they may continue to the left in various ways. So like they may be some number of previous vertices. And let me call this degree Li of V, if this vertex is V. Okay? So now this is the sum over V of the log for Li of V. So this is some kind of potential function that we need. We are going to assume that log of 0 is equal to 0 for this definition to make sense, because this could be 0. So basically we are summing up just over vertices which are actually endpoints. And now what we are trying to do so we want to devise a strategy for chooser that will prolong the game as long as possible. So builder introduces a new vertex, and builder provides a two coloring of the edges, of all the edges. And what does chooser do? The chooser has just two choices, either red or green. So chooser wants to keep this function as small as possible. So chooser chooses the color which makes this function as small as possible. And the important property is that basically the worst possible scenario for chooser is when half of these edges go in one color and half of these edges go in another color. And in that case, by the way how this function is defined, with every vertex V which currently is an endpoint of an I path, this function will drop by at least 1. So with a move of chooser, we are getting like this sum of the logarithms drops by at least 1 for each of those vertices V, for one of the choices. So for a random choice, it will drop by at least 1 in expectation. So for the better choice, it will drop by at least 1. Okay? And then there is a new vertex which maybe extends some paths, so something will get added, but what will get added, okay, so Vi, how does it change? We are removing the number of, we are removing an I, so we are decreasing by an I, but also what we add is at most the logarithm of 4 times the bound here. So let's assume that this number we want to have a lower bound of this number. So let's assume for a contradiction that this number never exceeds some bound that we want to put here, like n I minus 1. So we will get this upper bound comes here, right? The only problem is that we cannot guarantee this decrease with every move of chooser, because this function is defined separately for every I. And it could happen that a choice which works for one value of I is different, will be different from the choice that works for another value of I. But what we can do to remedy this problem is to use some kind of periodic strategy. So here we have an axis starting from 1 up to our d. Then we got our d minus a constant. This is where we start from. Yes, and for I equal to this value, we will be decreasing this every second step. So every second step, we will be decreasing the potential function for that. From all the remaining ones, every second step we will be decreasing the potential function from this. and so on, and so on, and so on. So basically, if we subtract, say, we look at d minus c minus j, then this function will be decreasing every 2 to the power g, maybe 2 to the power g minus 1 or g plus 1 steps, 2 to the power j plus 1 steps. Yes? And it turns out that it doesn't really matter, because see what we have. How much time do I still have? Okay, not much time. Let me now use the time axis. So consider, so we are assuming that we have some lower bound here. Yes. So there is a step when this value exceeded our lower bound, and we are going to observe how our function phi behaves. It has some value at this point, which is certainly a non-negative value. And every some number of steps, we are getting this decrease by n minus by ni. Notice also that this value ni can increase in one step only by 1. With one step, we cannot create more than one endpoint of an I-path. So if we are looking on the timeline, what was happening at time, like, I don't know, say that this is time t. So here we are looking at time t minus ni divided by 2. So our value ni here is at least ni over 2. Yes? So, and also everywhere here it is at least ni over 2. So this function, okay, it grows here by this value, but here there is a sudden drop by at least ni over 2. Here it grows, and here is a sudden drop. It grows, here there is a sudden drop, and so on. But here, we actually have an upper bound on the value of this function. The upper bound is ni times this, because this is like, we have that many summands, and each of those summands is at most this. Which is at most capital Ni times logarithm. Those drops are, okay, so so the value here, so the value of phi I here, it is at most Ni times log for Ni minus 1. Yes, this is phi I at this point, but on the other hand, it is at least the number of times we increase here. By how many we increase? We were always increasing by that much. And this is times the number of those steps where we were decreasing, which is something like Ni divided by 2 times 2 to the power, I don't know, 2 to the power d minus c minus I, something like this. And we also subtract those things, but this is how many times we make. We make ni over 2 steps, and in each step we are adding at most log for ni minus 1. So this is now our inequality. This term we can move here, which means that something like 3 over 2 appears here. So basically we can forget about this term. It doesn't really matter. This cancels out. This turns out to be not much important. It is just important that at the place where this bound is a constant, yes, so this is where this bound was just some starting constant, we should make this adjustment with this pi I often. So where this is small, we need to make it often. As it grows larger and larger, we can make it less and less often. And let's see what follows from this bound. From this bound, it basically follows that n to ni minus 1 is at least, we have something times ni and 2 to that power. Yes, so we are getting a tower function. This is how we are getting this tower function. And at the very end, we are getting a lower bound on n1, and n1 is just the number of vertices that needs to be played. Yes, because the endpoints of one path are just all the vertices. And this way we are getting the lower bound for on the clique game. Thank you.